Hey students, welcome to lecture number 11 of multiple zeta values and modular forms. So today we want to continue on talking about this formal double zeta space we introduced last time. So here in the overview we are here in section 4 where we talk about some connection of modular forms and double zeta values. And last time we introduced this space dk, which is a space of formal double zeta values, which means we have some symbols which represent these double zeta values and these single zeta values and their products, and we divide out relations coming from the double shuffle relations. And we proved some relations in this space, and today we want to continue on doing this, and then we will present a special realization for the space given by Eisenstein series, and then we will use our results to give some statements on modular forms. So recall that the formal double zeta space, denoted by dk, was the Q vector space spanned by symbols zk, zk1, k2, pk1, k2, which where these k's they sum up to this weight k. And so this zk you should think of being a single zeta, this zk1, k2 being a double zeta, and this pk1, k2 you should think of being the product of zeta k1 times zeta k2. And we divide out certain relations given by these relations here, which are effectively given by these double shuffle relations. So this is here the Stover product, and this is the analog for the shuffle product. So in this space, the only ingredient we can use to prove relations are these double shuffle relations. And using just these, we were able to prove the following last time. So when k is odd, we proved that any of these double z's can be written as a linear combination of these p's and these single z's. And you can write down these formulas explicitly. And using these zeta realization, this is what people usually call the parity result, meaning that in odd weight, there are no real double zeta values because all of them can be written as products of Riemann zeta values. And then using this, we were able to prove this theorem. So in the odd weight case, we were able to prove the dimension formulas for the space dk, which in the odd weight case is given by k plus 1/2. And also this theorem gave us two possible choices for a basis. So for example, one choice was we can choose the single zk's and all these p's, which comes exactly from this formula here. So by the definition of the double zeta space, the formal double zeta space, this lower bound was clear. But to prove this equality, we needed to show that that we can find a generating set with this cardinality. So in this case, we just needed to show that anything besides these objects can be written in terms of these. So, for example, these double z's can be written in terms of this basis. And then another choice of a basis is this set here with the single zk's and these double zk's, where the first entry is odd. And this we also proved by using this formula. So ignoring this term here because it's a basis element, we just needed to invert this formula here by using some argument modulo 2. And then, so this parity result followed from some more general lemma, and this lemma also implied a statement for the even weight case. So for even weight k, we obtained relations among these p even and these single z's, and we also gave explicit formulas here. For example, one simple consequence or special case of this theorem is that the sum of all p even is just a multiple of zk. And again, if we choose the zeta realization, this is just a classical recursive formula for single zeta values. And then we stated this theorem here, the analog for the dimension theorem, namely stating that the dimension of dk in the even weight case is exactly k half, where the basis is given by these Z odd odds. But this is not a consequence of this theorem here. Well, because there are no Z odd odds appearing in this. But one of today's goals is to prove this theorem here by using a little bit different techniques. Okay, so this technique we want to introduce is so-called gamma invariant pairing. So recall the space Vk is a subspace of polynomials with rational coefficients. So these are the homogeneous polynomials of degree k minus 2. And on this space we defined an action of GL2Z, but now we want to restrict or get an action of gamma, and gamma will not be GL2Z, but it will be PGL2Z. So it's basically, this is just a GL2Z modulo plus minus 1, so the identity matrix. But this here is now important that we choose. So in everything what we do today, k is always even. And then you can show that this is a well-defined action on this space here, because if two matrices just differ by a minus sign in the determinant, then you see, because these are homogeneous polynomials of even degree, then this factor doesn't matter. And on this space Vk, we now define the following pairing. So the bilinear pairing, so we need to define it on the monomials. So if we take two monomials, for example the monomial x r minus 1 y to the s minus 1 and x to the n minus 1 and y minus 1, then we define the pairing of these monomials to be this Kronecker delta here. So this is 0 if these two sets are not the same, so meaning what we just have one term when this is 1, namely when this r equals this n, and when this s equals this m. So there's a switch, you need to be careful here. And then we have some factor here. And one should say that this k is here always r plus s and m plus n. Okay, and this pairing has nice properties with respect to this action of gamma. Namely, it's gamma invariant. So maybe first of all I should write down here recall the action. If gamma, small gamma, is a matrix ABCD, then this action here is defined on a polynomial like this. So this we used last time to prove this lemma. And now the statement is that this pairing here, first of all, is symmetric, which again uses that the weight is even, non-degenerated. And the most important point is that this pairing here is gamma invariant. And this is part of the exercises, but you can check directly by using the definition of this pairing that the weight is even, that this satisfies these properties. And this we now want to use to prove relations. But first, recall, we used this action last time to describe these double shuffle relations in a different way. So first of all, what was the connection of this formal double zeta space and these polynomials? So they appeared when we considered the generating series of these symbols. So the generating series of these symbols zk1, k2 was denoted by this zk. So this is a polynomial of homogeneous degree k minus 2. And this we viewed as an element in dk tensor these polynomials vk. And the defining definition of the formal double zeta space could be written by using this generating series in this way here. So this here is the generating series of the product, which I didn't write down. But here we see the generating series of these double zk's. And also here, so the first line here is the Staffel product and the second is the shuffle product. And using this action, we could write these equations. So this equation here, we can write like this. And here I should say, so recall this epsilon was a matrix given by this. So if I let this epsilon act on some polynomial, then it just interchanges x and y. So we see here that this part is exactly this. So the identity matrix doesn't do anything, and this epsilon interchanges x and y, and this rk is this. And here, this corresponds to this, because the matrix T was given by this matrix. So if I let T act on something, then I get exactly x plus y, comma y. And T epsilon is just this matrix. So it just changes the columns, this multiplying with epsilon from the right, and therefore this action here is exactly this. So this equality here is just exactly this by using this group action. Okay, so and now we further want to write this in a shorter form. So for this we introduce now the following element, delta. So you see delta is now, so this is an element in the group ring. Oops. I mean, already these elements are elements in the group ring, so we don't last. Maybe I should have said this here. So this is not just an action of gamma, but we let the group ring that gamma act on this space, meaning we consider a formal linear combination of these matrices, and then just extend this action linearly. So here, if I have a linear combination of matrices, so this plus is a plus in the group ring. It's not, I'm not allowed to add these matrices. It's just a formal combination. And this here is also an element in the group ring. And you see that T times 1 plus epsilon is this part here. And here we have minus 1 times 1 plus epsilon. This is this part here. So if I put this on the right hand side, then what I have there is exactly the equation that oops. So I have exactly this equation here, that this is just equivalent to this single equation here, because I just put this on the right hand side and then define the gamma as a delta exactly like this element. So now this equation here can be written as this simple single equation, meaning letting this element delta act on the generating series of these double z's should equal the generating series, this rk here. So it's just these single z's. And now we want to use this pairing, and so let psi be an element in the group ring. Then we want to define its joint action as a anti-automorphism induced by taking the inverse of matrices. So this just means that, for example, if I have an element AB in the group ring, A times B, let's say this is psi, then psi star is anti-automorphism, means I need to reverse the order and take the inverse. So this is this. And then the statement is that using the gamma invariance of this pairing, we see that whenever I have so f and g are in Vk. So if I have the pairing of f where I slash this xi and take the pairing with g, then I can take this adjoint action and let it act on the right of g, and I remove it here from the f. And so this has a nice effect that, so if I have this equation here, and if I pair this with any f, in VK, so if I pair both sides, well, it's symmetric, so I can also do it like this. And then I can construct the adjoint of this delta, which is just given by this, because I just need to reverse these here and then take the inverse. So this means that for any f, I get a relation among elements in the double zeta space by considering f, and then I'll act this delta star, and here I have zeta k equals f r k. So this here is gives the same. I mean, this here is the same because of this equality here, and because in the double zeta space this equals this, so this is the same. So we really get a relation in the space of the formal double zeta space, but by starting with any f. So you can start with your favorite polynomial, homogeneous polynomial of degree k minus 2. Then you can let this element delta star act on this. This gives you again a new polynomial of degree k minus 2. And then you can take the pairing of this polynomial with this generating series. So in other words, this will give you some linear combination with some coefficients of these zk1, k2. And then because this equals this, and we know that this equals this rk, we also get this equality here. I mean, this is just the same. So we get really a relation that this is some multiple of zk. So starting with any f, we get a relation among these elements by just applying this fancy element here to this f. So, and now let's go back to what we actually want to do. So we want to prove this theorem here, and for this, so we want to show that these z odd odds are a basis, and therefore we need to write anything in the space as a linear combination of these z odd odds. And what we, for example, already know is that zk, so we had this odd sum formula which stated that 1/4 of zk is the sum of all zk1, k2, where both of them are odd, and k1 is greater or equal to 3. So zk can already be written in terms of these, but what we don't know so far is how to, for example, write a z even in terms of these elements. So how do we write this as some linear combination of z odd? And if we know this, then we also know how to write p even, because they can be written as a linear combination of these. And p odd is already clear by the Staffel product. So the only problem is to find a relation of this form here, where we maybe can also add some multiple of zk, because zk can already be written in terms of these z odd. So we want to find a relation of this type to prove this theorem. So in other words, we now have an ingredient to get a relation, but we want a really special relation. We want to have a relation where here in the double part, these k's are odd, but for one case we want the even. So for example, if we give m and n even, we want to find an fmn such that the double part here is everything is odd except for this one even, so that we have this relation of this type, and therefore we can write this on the other side and then express this zmn in terms of odd and zk. Okay, so in other words, to rephrase it even more, so we want to find an fmn such that if we let this delta star act on this fmn, this is a new polynomial, And the even part, or more precisely the odd part, because here in the generating series, if the entries are even, then because of this shift here, the polynomial is an odd polynomial. So the odd part of this polynomial should be just one term. And so the statement is that we want to find fmn polynomials of homogeneous degree k minus 2, where m plus n is always k, and m and n are even, such that the odd part, so this pi odd here, is the projection to the odd part, which is 1/2 1 minus delta, and delta is minus 1, 1, 0, 0. So we want that this odd part is exactly this single monomial here, because if we pair this with the generating series in DES2, then this picks us out exactly our ZMN, because M and N are, the pairing reverses these things here. So in other words, if we can find FMN with this property, then this relation we get out of pairing this with the generating series Z zeta k gives us a relation of this form here, where everything in DES2 is something with odd, except for this one single even. And this part here just gives some multiple of zk. Therefore, if we then put this on this right side here, we can express z even in terms of z odd. So we want to find these special polynomials fmn with this property here, because this will then prove our theorem. And this can be done explicitly, and we want to do this for all m and n at the same time, for all weights. And to do something for all weights at the same time always means we want to work with generating series. So now it's maybe a little bit confusing, but so we want to find polynomials for each m and n, and these polynomials are polynomials in x and y. So therefore, if we consider all of them at the same time, we will deal with a generating series in 4 variables. So these m and n are now the variables for this m and n, and the coefficients are given by polynomials of homogeneous degree m plus n minus 2. So this shift here is maybe not important, but basically we are just interested now in generating series in these 4 variables, and we will see that that we can write down explicit generating series for these fmn, which then satisfy the property we want. And to do this, we start with this generating series here. So so this is now f small fm, x and y. So this is now an element in this here. So, or you can also just think it's a formal power series in these 4 variables with rational coefficients, which is given by these products of hypergeometric of these hyperbolic trigonometric functions. So we have this hyperbolic cosine here, and the hyperbolic sine, and the hyperbolic cotangent. What they are is just, so the hyperbolic cosine is basically just the even part of the exponential, and the hyperbolic sine is the odd part. And this hyperbolic cotangent here, together with this factor here, is basically just the generating series of the Bernoulli numbers. So this guy here is just an explicit generating series in these 4 variables, where the coefficients can be written down explicitly in terms of binomial coefficients or factorials and Bernoulli numbers. And with this generating series, which comes somehow forth from the sky, but this is basically the generating series of so-called of Bernoulli polynomials. maybe just written in a little bit fancy kind of way. And with this, then the definition of the generating series of the capital Fm, what we want, so which we denote by capital Fm xy. So this is again an element here where we call the coefficients Fmn, and this we just define as a combination of these small fn. And if we would extend this this group action also on this space here, so we could also define the group action of gamma on this space by just letting it act here on these variables x and y, then this you could also write just as Fmn, where we slash with 1 plus epsilon minus st. But maybe this is not important, it's just we take an explicit combination of this generating series here. And then the statement is that this Fmn satisfies exactly what we want, and the statement of the lemma is the following, that maybe I should recall what we actually want. We want that this Fmn satisfies this property here, meaning if we slash with this special element here, then we just have this one monomial, because we want this one monomial to pick out these z even, this Zmn. And therefore, what we now in the generating series case want, we want the generating series of these guys. And this is exactly what we get. So if we let this special element here act on this generating series, then by using just this explicit formula, you see that all of these horrible formulas, they collapse to this really simple, nice term here, which is now just a product of the hyperbolic cosine and the sine in m and n. And if you write down what this actually is, this is just the generating series of this one monomial which we want. So therefore, if we compare the coefficients of this side and this side, we get exactly that these Fmn satisfy this property we want. And therefore we get explicit Fmn in this Vm plus n, such that if we slash it with delta star and then take the pairing with the generating series of these double z's, that we get exactly this linear combination here, where everything is odd except for Zmn. And therefore this Zmn can be written as a linear combination of Z odds, because Zk can also be written in terms of Z odd. And this can be done explicit. So everything here is quite explicit, even though maybe it's a little bit mysterious if you do it in this way. But the formula we get is the following, which in the end is maybe not so horrible anymore. And this was first done by Gangel, Kaneko, and Sage. But the proof we just saw is maybe a shortcut version of their proof. But we see that for even m and n greater or equal to 2, and k equals the sum of these, this Zmn can be written as an explicit linear combination of Z odd plus some Zk's, but these Zk's can also be written in terms of Z odd, and therefore what we also can then obtain, maybe these formulas are now not so nice anymore, but any Zmn, m and n even, is an explicit linear combination where you can write down these coefficients in an explicit way of Z odd, and then using that whereby the Staffel product Pmn is just Zmn plus Znm plus Zm plus n. So using this formula together with this, we then get this formula here. So also this P even can be written in terms of Z odd, and therefore everything in even weight can be written in terms of Z odds, and therefore we have our theorem here that the Z odd form a basis of the space dk. Okay, So this is this, and but now, so one of the goals of today is also to explain this part in the Brottos-Cramer conjecture where we had this, I will come back to this later, but there we had this term OX squared minus SX, which somehow said that in DES 2, there are relations among zeta odd odds which come from cusp forms, and this we now want to show in this setup here by presenting some realization for this formal double zeta space in terms of Eisenstein series or combinatorial double Eisenstein series, and then use this result here that any product of Eisenstein series, where we know that they span the space of modular forms, can be written as a linear combination of these double Eisenstein series, and then we will see that sending Q to 1 will give us relations among these zeta odd odds. But first, before we do this, we need to talk about realizations for all k's at the same time. So last time we talked about realization of dk in some vector space A by saying that a realization of dk in some vector space A is an homomorphism from dk to A. But now we want to consider all k at the same time, and we will also replace this vector space A by a Q algebra, and we want to say that the realization of D without a small k here in some Q algebra A is now a collection of these realizations for all weights. And why do we want this? Because, so one example is, for example, this zeta realization. So there we had a realization for all weights, and also our A was in this case just the real numbers. And we want this this additional product here to now make some statement that if we have a realization in some Q algebra A with some additional properties, then we can obtain some classical results for zeta values and for modular forms. But first, how do we actually construct a realization for all k at the same time? So how do we do this for these zeta realization? Well, in this case, we use these shuffle regularized multiple zeta values and considered their generating series, and then saw that the functional equation of the generating series implied that for each weight k we get a realization in the space of multiple zeta values. And this works in general, so by using this following lemma. So we want to find a realization in some Q algebra A, and this we can do by considering generating series. So again, consider formal power series with coefficients in A, which we denote by P, Z, and Z, such that they satisfy this equation here. So, and this is exactly the equation which was also satisfied, which we denoted by T shuffle X and T shuffle XY. So the generating series of shuffle regularized multiple zeta values. And then you get a realization phi by defining, well, here I should also say, so a realization is a collection of phi k. So, and each phi k is a homomorphism from dk to A. So we can say what we mean by phi k of zk. So this is an element in A, and also phi k of zk1 k2. This is an A, and similar for P. And but if we have a realization for all k, what I will leave out this k here, because the weight k becomes clear from this index here. So the notation is here that if we have a realization for all weight k, this makes sense here by saying phi of something in weight k means this is phi k of this element. So therefore, if we now have these triples of power series with coefficients in A satisfying these functional equations, then we can define a realization of D in the Q algebra A by saying that the phi of zk is just the coefficients of these z's, except that in weight 2 we need to correct, similar to the shuffle regularized multiple zeta case, because in the double zeta space this z2 is always 0, and the image of phi on zk1 k2 is just the coefficient of this monomial here in this power series, and the image of phi on this p is just the coefficient of this p. And this defines this phi for all weight k's, and therefore we get a realization of D in A. So if you want to construct a realization, we always just need to construct generating series with coefficients in our Q algebra A, which satisfy this property here. Okay, but here at this point we still didn't need that A is actually a Q algebra, but we will see now that in all cases we consider A is a Q algebra, and we also want an additional property, namely that this P has to do with the product of these single z's. But it will not always be exactly the product, but maybe with some correction. And yes, so this is the statement of the following, maybe a little bit too long theorem, but so maybe I first should make this a little bit smaller first. So assume we have a realization of D in a Q algebra A, and then we introduce the following notation by writing zk to be the image of this zk. But now we also include an element in weight 2, where this z2 here is some element in A. So this is not a statement yet, it's just a notation. And now the first statement is that, so assume that we have a realization such we can find z2 like this, such that the image of this P is actually exactly the product of these z's. Then we can show that this zk is always a polynomial in z2, and moreover we can give an explicit formula for these even z's in terms of some Bernoulli numbers and this. And of course, so if we take the zeta realization, meaning if we send, so maybe let's say this is a zeta realization. In this case, this pk1 k2 exactly was zeta k1 times zeta k2. So it satisfies this property with the additional, so with this z2 here, or maybe I should write it like this, z2 was zeta 2. So we had this property here. So this realization satisfied this property here. And what is the consequence here? Well, this is just the Euler's formula for the even zeta values. So this is the first statement of the theorem. And now the second statement is a little bit longer. So now, so second statement here. Now assume that that we have a derivation on A, this partial here, such that the product, so the image of P of this realization, is not exactly given by the product of these sets, but we have some correction term including this derivation on this algebra A. Then the statement is that for even k, this zk is always a polynomial in z2, z4, and z6, and moreover, this derivation on these z4, z2, z4, and z6 can be written down explicitly as a polynomial in Z2, Z4, and 6 again. So in other words, meaning that this polynomial ring here is closed under this derivation. And also we have a differential equation for this Z2, but this part here basically follows from these three. And therefore, in other words, this polynomial ring here, Z2, Z4, and Z6, is the same as this, where we can also choose Z2, the first derivative, and the second derivative of Z2. And this condition is actually also satisfied by the zeta realization, by taking the derivation to be just the zero map, because then these parts here vanish, and then we have this condition here. And also here, well, then everything here is zero, and we get the same statement as before. But people familiar with modular forms, or also what you did in your exercises, these differential equations are also true if zk are given by the Eisenstein series. And these here are usually denoted by the Ramanujan differential equation, and this here is often called the Chezy equation. But even though we have this theorem, which we didn't prove yet, but assuming this theorem is true, we still cannot prove this for the Eisenstein series because we don't have a realization yet with this property. But this is one goal of today, to actually present a realization which satisfies exactly this property here, but which do not satisfy this property here. So here we can also see, therefore, that in this realization we will see that this product, these p, k1, k2 is actually not exactly given by a product, but by some correction terms. But for any realization with this property, we can show that this satisfies then the Ramanujan differential equation and this Chezy equation here. And also, the third statement of the theorem is that, well, assume that maybe in the case when the k1 and k2 greater or equal to 4, that in this case the p, k1, k2 is given by the product of the z's. Because here in this case we saw that we just have these correction terms when k1 and k2 are 2, then we can show that all these zk's are actually polynomials in z4 and z6. And again, of course, this is the statement that we already saw, that gk is also a polynomial in g4 and g6 for k greater or equal to 4 even. And therefore, using this theorem later, we will prove these things in a purely combinatorial way by finding the correct realization of this space D in the ring of formal power series with rational coefficients. Okay, so what is the proof of this? So the proof sketch is that all statements here actually follow from the theorem at the beginning. So let me recall this one. So this theorem here, which we proved last time, which gave us relation among p even and z even, and for example one implication of this theorem was this one here. So, but here you can already see that the proof of the first statement of the theorem there somehow follows from this, because if this p here is a product of these z's, then we get some recursive formula for even zk's in terms of even zk's with smaller k's, and therefore we see that any zk then can be written as a polynomial in z2. So, and also we can, I mean, this is just one simple case of this theorem here, but we can also combine these here for different k1 and k2, and I make it precise in the lecture notes. such that we can erase here the P where the J is 2, or the K minus 2 is 2, so we can choose two different choices for K1 and K2 and get a relation among P even where both entries are greater or equal to 4 with zk's, and this is then used for the third statement of the theorem. Yep. So again, the idea is to use this theorem from which we get this recursive formula here, and so in the theorem we had that the sum over all these P even is given by zk, by k plus 1 over 2 zk, so here we put this there, and then for example here for the second statement we can replace this here with the products of these z's and maybe some correction term with the derivative, and then we see using this formula we inductively get the statement here, and also this can be proven directly by using this together with the theorem before. But yeah, so this maybe you can look up in the lecture notes, but this follows directly from everything we already saw. But the interesting question now is, of course, what is this realization here? Can we find a realization which actually has a nice application by using number 2 and number 3? So this is the goal of the remaining time. Find a nice realization of D in the space of Q series with rational coefficients such that the image of zk equals the Eisenstein series, and remember the Eisenstein series was minus bk, so we now assume k is even, plus our Q series G. Oh, and here's also a factorial. And this we also write just by beta and gk. And so we will actually, to construct this realization, which we will denote by phi g, we will actually construct two realization, one for this beta and one for this k. And then one important point for realizations is, so here is again the definition of realizations, they are all just families of homomorphisms, and if I have two realizations of D in some Q algebra A, then I can also add them, because of course these things are just groups, and therefore I can add two realizations and get again a realization. So here we can separate this problem of finding this realization by finding a realization which we call phi beta. So this will be phi beta of zk plus and phi small g of zk. So we will find these explicitly and then sum them up, and we will see that then we get this Eisenstein realization, which satisfies exactly the properties we want. And we will start by finding this realization here. And again, how do we find realizations? Well, we need to use this lemma here. So to define a realization, we need to find power series satisfying certain functional equations. And if we want to find, now for example, if we want to find our phi g, which in depth 1 should be just given by this Q series G, then we need to consider this Z to be the generating series of this G, and we construct this generating series in depth 2 explicitly out of this. So let's do this. So we now want to construct these two realizations. And for this, recall the generating series of our Q series G was denoted by this German G here. And for this, we already proved what happens if I multiply two of these generating series in depth 1. And so maybe let me recall, we proved, or this I think was one of the exercises, was to show that if you multiply them in depth 1, then the shuffle product for these guys comes from this equation here, and the shuffle product comes from this equation here. And this we can rewrite now a little bit by introducing the generating series of the betas. And then we can see, maybe, well, it takes some time to see this, but this is now just rewriting what we already proved. So here in the first line, the statement is that this can also be written like this. And for this, we just use these terms here with this exponential, and which are basically given by the generating series of Bernoulli numbers. And therefore, if we define this b by basically given by this part here up to some, so removing here the pole and also some constant term, so this b will actually be the generating series of our betas. But using this equation here is just another way of writing it like this here. So you see that here the first part is exactly the correct, so it's the shuffle product formula, and here's some rest. And this part here, what we already proved is just exactly this, by just introducing a notation for this part here. So this G prime is just the generating series of the derivative of this Q series G. So with this lemma, we have two expressions for the product of the generating series for our Q series G. And maybe I could take the lemma down here. So let me copy this lemma. Maybe erase this. So the goal is to get something which satisfies this equation, and what we have now, we have something which satisfies this equation. So and in the generating series Z should be given by these small g's. So this part here is already what we have here. And now the goal is to define the correct Z such that we get this equation here. So this Z here will be this part here, and we will also take some parts from here to use all of this to define this Z here. In such a way that this Z is also this with parts here, and also that this part gives this, plus some garbage terms here, and this and this. And this can be done in an explicit way, and maybe it takes some time to find this solution, but then using this lemma, it's easy to see that it's true. So the statement is that if we define, so this is now the Z, so if we take this G in depth 2 plus these correction terms, then we see that we have this equation here, where this P is given by this here. And so we see the P is not exactly just the product of these G, but there's some extra terms here. And this is just by using this lemma here. So to check that we have the first equality, you evaluate this product by using the lemma, the first line of the lemma, and to get this equality here, you use the second line of the lemma. And therefore, we have a triple now of generating series which satisfy the conditions in the lemma, so the P, this H, and the G, and therefore we get the realization phi G, which satisfies the property that phi G of ZK is exactly our Q series G. if k is not 2. Okay, but here the p is given by this. It's not exactly the product, and it's also not something satisfying the conditions in the theorem, because there are more error terms. But we will correct this with the betas. So this is now somehow the non-constant term part of our realization phi g we are looking for. So we need to find now the realization phi beta, and then the sum of this phi g plus the phi beta will give the phi g. And this can be done also explicitly by using this theorem here. So the statement is that if we take this generating series beta, which was given by the generating series of Bernoulli numbers, or explicitly by this, then we can write down this explicit def2 part here, and then you can see that this also satisfies this relation here. So in other words, this gives a realization phi beta such that phi beta of zk is exactly this beta k, which again, this is just minus bk over 2k factorial. And well, this you can check by directly using this definition here, but what's behind this is also the following. So if you consider this function here, which is so the beta plus some pole, so this is just given by the hyperbolic cotangent, and the reason why this construction here gives this formula here is that this cotangent satisfies the following property, which is sometimes called the Fay identity, and we will see later that, for example, if we write gxy given by the product fx fy, then this identity here can be written by using this group action as 1 plus u squared equals 1 over 16. And therefore the reason why this works here is that the hyperbolic cotangent satisfies this equation here, but this equation just means that we have this equation, and we will see later that every time you start with something satisfying this equation plus some small additional equation, then you can actually find a realization by this construction for this D in Q, or not in Q, but in wherever the coefficients of this G are. And this has to do with period polynomials of modular forms, which we will discuss later, but the statement is basically that period polynomials of modular form satisfy something like this, and therefore every period polynomial of a modular form gives a realization of the space dk, where k is the weight of the modular form, in some Q algebra A. Okay, and so now we have two realizations, the phi beta and the phi g, and we see that here, so actually here, this this part here is what we denoted by pxy. So in this case, the product is exactly given by the product of the betas, and we see that if we add this to this one here, so what is phi g of p k1 k2 plus phi beta p k1 k2, then we see that to this term, so maybe let me write it down. So here we get g k1 k2 g plus beta k1 g k2 plus beta k2 g k1. So this comes from this part here. Let's ignore this part here. And now from the beta we get plus beta k1 beta K2, but this is exactly just beta K1 plus GK1 times beta K2 plus GK2. So in other words, this is just a product of the Eisenstein series GK1 times GK2. And therefore, and this will be what we define in a second, the realization phi capital G of P K1, K2. But we still have these extra terms here. So we will have this product of the Eisenstein series plus the derivatives in the case when one of these are 2. And then we will see that this exactly satisfies the condition number 2 and 3 in the theorem we had before. So let's define this realization, and this will get a special name. So we will call this a combinatorial double Eisenstein series. So we define this realization, as I said before, phi g as the sum of these two realizations given in the theorems before. So they are explicit. So these phi g are given by explicit rational numbers, and these phi g are given by explicit Q series with rational coefficients. And then we get this realization because we are allowed to add realizations. And the combinatorial double Eisenstein series, what we mean by this is the image of this realization on these double Z K1, K2. So in other words, they are given as the coefficient of these generating series given in these two theorems where we had this B, this double B, and this H there. And then we get, as I just did before, that the phi g of these products is actually then the products of Eisenstein series, and also that phi g of k of zk is exactly gk if k is not 2. So we see that the product here is given by the product of Eisenstein series plus this correction term with q ddq, and q ddq is a derivation on this ring here. And in depth 1 we have this, and therefore this realization here satisfies exactly these conditions in this big theorem, namely it satisfies actually this condition here, and it satisfies also the condition here, because these extra terms just appear if one of K2 or K1 are 2. And therefore we obtain this differential equation and also the statement that Eisenstein series are polynomials in G4 and G6. Okay, and then one proposition which is actually a quite easy consequence. So the statement now is that these combinatorial double Eisenstein series are actually also modified Q analogs, by which we meant that if we multiply by 1 minus Q to the weight and send Q to 1, we get exactly back the corresponding zeta value. And this just follows from the fact that we already know this for these Q series G. And this follows actually from this, because in the definition of these combinatorial double Eisenstein series, well, it's given by these, and therefore these H are basically given by these Q series G, but one can show that all these remaining parts actually vanish under the limit Q goes to 1 if you multiply by 1 minus Q to the total weight, and therefore just this has any contribution to this limit, and therefore the limit of these combinatorial double Eisenstein series is just exactly the limit of this small g, where here this k is just the sum of these 2k. And now we can use this to explain why are there relations among double zeta values zeta odd coming from cusp forms, because we also learned that modular forms are also modified Q analogs of their constant terms, and cusp forms have zero constant term. Therefore, if I start with a cusp form, then we know that any cusp form is a modular form, and any modular form can be written as products of Eisenstein series, and of just two products. And then we know that, therefore, using this realization, any P even can be written in terms of Z odds. This is true for any realization, and therefore any products of Eisenstein series can be written as a linear combination of G odd, and then taking the limit, we get a linear combination of zeta odd. But because this linear combination of G odd is a cusp form, this linear combination of this zeta odd is given by the constant term of this cusp form, which is 0. And therefore this gives the relation among zeta odd. And therefore we get an explanation of this term here. So if we multiply this out, then in the depth 2 case we had this term OXX minus SX, where SX was the dimension of cusp forms, and where in the lecture notes I do it in more detail, and also next time we will see a different explanation using period polynomials. But what one can do is, one knows that there's an explicit basis of modular forms in terms of products of Eisenstein series, and because in our realization, so these are now greater or equal to 4, and in our realization we know that any product can be written in terms of Z odd, this is what we showed at the beginning, and therefore any modular form can be written in terms of G odd. So in particular, this can be used to write down an explicit basis for the space of cusp forms in terms of these combinatorial double Eisenstein series in the case odd. And so, for example, in weight 12, the space of cusp form is spanned by this linear combination, in weight 16 by this, and these coefficients, they can be written down explicitly by using these explicit formulas we calculated earlier. And therefore we get explicit relations among zeta odd by now multiplying this with 1 minus q to the weight 12 and then send q to 1. Because this then gets sent to the constant term of the cusp form, which is by definition 0. And this is all we wanted to do today. So next time we will then start with period polynomials and also explain these type of relation in a different way, and then also explain this other construction I mentioned here, where I said that any object satisfying this equation somehow gives a realization, and this also has to do with period polynomials. See you then.